So we've had a little bit of an introduction to discrete random variables and probability density functions. And remember, a probability density function needs to meet two criteria. The first one is that all of the probabilities add to 1. So we've got to make sure that we've got all of the potential outcomes listed. And then second of all, we've got to make sure that we have no negative probability, because that just doesn't make any sense. What we're going to do in this video is take a look at some slightly harder examples, but using all of the same concepts which we looked at previously. So we've got a first example here. The discrete random variable x has the following probability density function where k is a constant. And we've got this, the distribution table down here, and we need to find k. So because it's a probability density function, that means that if I add all of these probabilities up, they have to be equal to 1. So if I add 2k and 0.1 and 3k and 0.15 and 0.25, because it's a PDF, because it's a probability density function, this must be 1. And now this is just a linear equation which I can solve if I group my k's. I get 5k, and if I group my constant terms, what do I get there? Just 0.5, which has to be equal to 1, so take 0.5 from both sides, and we get that k is 0.1. So what does that mean? Well, if I erase just this bit here, that means that instead of a 2k, I can write 0.2, and I've got my 0.1, here I'd have 0.3. Okay, so all of those, they would add to 1, which we've just seen. So we found what k is. Now we need to use our probability distribution table to determine the probability that x is greater than or equal to 2. So there's two ways we could do this. The first way is I could add 0.1 and 0.3 and 0.15 and 0.25. And if I did that, I would get 0.8. Alternatively, I can just do the complement, 1 minus the probability that x is strictly less than 2, which is the same as 1 minus the probability that x is 1, which is just 1 minus 0.2, which we see is 0.8. So whichever way you choose to do it, totally up to you, but it's good to be aware of both ways. And then finally, just give ourselves a little bit of room, we've got to find the expected value of x. So remember, that's just the sum. So the expected value of x is just the sum of all of my x's times the probability that they occur. And well, that's just going to be 1 times 0.2 plus 2 times 0.1 plus 3 times 0.3 plus 4 times 0.15 plus 5 times 0.25. And if we put that into a calculator, we get 3.15. So that's just an example of a slightly different question that you may come across. We're going to have a look at a couple more now. So let's come over to a second example. So the discrete random variable y, so I've just changed the letter here, has the following probability density function where a and b are constants. So here's our probability distribution table. And it says that if the expected value of y is 2.3, can we work out what a and b are? Well, the expected value of y, if we were to calculate that, that's just 0 multiplied by the probability that it occurs, so a, plus 1 times the probability that it occurs, which is 0. And you continue to do this all the way down the line. So 2 times 2a, and 3 times b, and 4 times 3b. And well, if we were to add all of those up, so we've got 0 here, 0 here, we've got 4a there, so 4a, and here we're going to end up with a total of 3b and 12b, so we're going to get 15b. And it says that this has to be equal to 2.3. But I can't solve that for a and b because I've got two variables and just the one equation. So I'm going to need to generate another equation from somewhere. And I can do that because it's a probability density function. All of these probabilities have to equal 1. So if I add all of these up, so add all of my a's, I just get 3a. And I add all of my b's, I just get 4b. That has to be equal to 1. And so now I'm just solving a set of simultaneous equations. So if we come down and we have a look at this, if I subtract one equation away from the other, so I end up with just A and 11B and 1.3, then I can get an expression for what A is in terms of B. And well, if I just pop that in for one of my equations, so if I take this and I pop it into here, I get 3 lots of 1.3 take 11B. So instead of writing an A, I write my new expression, plus 4B is to be equal to 1. And I just solve this. So I end up with 3.9 minus 33B plus 4B is 1. So if I subtract 3.9 from both sides, I get negative 2.9 over here. Negative 33B plus 4B is just negative 29B. And so B here would just be 0.1. And so if B is 0.1, then I put that into this equation again, or I could even pop it into here, right? It doesn't really matter. So A would be equal to, so if we pop it into here, 1.3 minus 11 lots of 0.1, so that would be 1.3 minus, not equals, sorry, minus 1.1, which is just 0.2. So I've worked out that B is 0.1 and A is 0.2. Now that's important because that means that I can rewrite what all of these probabilities are. I know that the probability of, is 0, so my A is just 0.2, 2A would be 0.4, a B would be 0.1, and a 3B would be 0.3. And if I add all of those up, I just get 1. And I'm just going to erase this bit here, just this top line, so it's not in our way. Okay, now we have to find the probability that Y is greater than 1, given that Y is less than 4. So for it to be less than 4, we're strictly looking in this space here. So the total probability available there, so the probability that Y is less than 4 would be just 1 minus the probability that it was 4, or you could add all of these together. Again, it doesn't matter, you're going to get 0.7 no matter what way you do it. And well, the probability that Y is greater than 1, given that we are less than 4, well, the only options available now for Y to be bigger than 1 are just these options here. We can't have the 4, so it's just 0.5 out of 0.7. So our probability here is 5 over 7, or just 0.7143. If we look at a third and final example, so the discrete random variable t, so I've just changed the lettering again here, has the following probability density function. So that's this distribution table down here where k is just a constant, and we need to try and find out what k is. So if we were to add all of these probabilities up, because it is a probability density function, it would have to be equal to 1. So if I add all of these up, and 0.5, that has to be equal to 1. So k squared plus 0.5k plus 0.5 is equal to 1. Now we have to try and solve this equation. So if I subtract 1 from both sides, I end up with this equation. So I now end up with minus 0.5 is equal to 0. And that's really important because we know how to solve these quadratics for the roots of quadratics. So if I multiply everything through by 2, I just get 2k squared plus k minus 1 is 0, because 0 times 2 is just 0. Now I can use slide and divide, or if you have your own different method to solve these equations with this constant out the front, you can use that. But I'm going to use slide and divide. So I slide my 2 down here, and I get just k squared plus k minus 2 is equal to 0. So this is just a multiplication down here. So that's my slide. Then I factorize. So I can now factorize this into k plus 2, k minus 1. Then I divide by my 2, which I slid down there originally. And then I simplify. So 2 over 2 is just 1. And well, this half I can't simplify, so that just stays as it is. And then I lift any bottoms up, so I bring my 2 out the front here. So I end up with k plus 1 and 2k minus 1 to be 0, which yields me 2 solutions. K to either be -1 or k to be 0.5. Now, not both of these solutions are correct because it's a probability density function. I cannot have negative probability. If I chose k to be -1, then this one here and this one here are both going to have negative probability. So we cannot have that. A probability density function always has to have positive probability. So k to be 0.5 would be the correct answer here. So here we would get 0.25. Here we would get 0.1. Here we would get 0.15, and here we just keep at 0.5. So if you were to add all of those together, you will see that you get 1. So if we added 0.25, 0.1, 0.15, and 0.5, we just get 1, which is what we need. So k is 0.5 in this case.